Hello, am I audible? Uh, yes, am I audible? Hello, hello. Okay, I think I am audible. So, okay, we'll wait for just 2 minutes so that if somebody else wants to join, then we can start this session, today's session. Okay, so just 2 minutes, and we'll start. Okay, so I think we can start with this session. Anyway, this session is recorded, so you can see it later. So today I will be talking about week seven lectures. Whatever we studied in week seven, and since it is linked to the week six, so I will be linking both of them, and then together we'll be learning about whatever the concepts we learned in week seven as well as week six. So, as we started with in week six, we started with temperature on of controller. So we'll start with that only, and we'll go through that the control system, and the feedback circuit. Then we will slowly realize each and every block uh, using opamps. Then we'll go deeply into some of the blocks which were being taught in week seven, like heating circuit and controllers. Okay, so um, the aim of this, so we had to design and build a temperature on of controller. So this was our main aim. So how we can use this? How we can realize this using our op-amp circuit? So we will look again, and so basically in this we learned that there is a control system which is used here, consists of controller, then our heating plant. This is the plant for which we are like basically controlling the temperature, heating plant. Hmm. Then, so this is the output, and then we are feeding back it to the our sensor and signal conditioning circuit. Sensor and signal conditioning circuit. Then this signal is fed back to this controller. So this is our system. We can say system input. This is our feedback signal, and here it is error input. So this error we are giving it to the controller. So based on the error, it is giving instructions to the heating plant. So accordingly, heating plant temperature is changing. So this we saw this in week 6. So this was an error controller circuit. So each and every block we saw that we can realize this using opamps. So as a controller and heating plant, we will see separately in this week 7 series lecture series. But then just for the sake of revision, I want to tell that implementation, we implemented this error input, implement this error signal, this error block also we implemented. Sensor and signal conditioning circuit also we implemented. So how we implemented, we will just have a look and then we'll go towards the controller and the heating plant circuit. So implementation of error detector. So since error detector is basically subtracting two signals, so we need a summer which can subtract two signals. So for that we used an op amp. By the way, if you have any doubts, you can ask in between regarding assignment questions. But assignment questions, I will be discussing that in the end of this, after ending this revision, and then we'll go with some extra questions also. But if you have some doubts till week 7, then yeah, you can anyway you can ask whenever you want. So yeah, so we were looking at this error detector circuit. So we realized this using a simple differential amplifier, which, which basically differentiates the input signal that we are giving it. This is V1, this is V2. So these two are in two input signals, and we give it to a differential amplifier having a gain of 100K. This is all the resistors are equal. So this we can consider as our system input, and this we can consider as our error feedback signal. So the output which we'll get here, it will be the error signal. Error signal. Now we also saw that uh, sensor signal conditioning circuit. So we were able to realize this. Then we also realized the sensor signal conditioning circuits. So for that, what we did, implementation of sensor signal conditioning circuit. Yeah. So as we know that we are feedbacking this signal, the output signal of this heating plant back to the controller. So for that we need some sensor which can detect the signal, the whatever we are whatever we are getting at the output. So for that we use LM35, that is a temperature sensor, and it was based on the temperature. So its sensitivity is given by sensitivity is given by zero point 0.1 volts per degree Celsius. So for every zero point 0.1 volt change in the output, in for every 1 degree Celsius change in the heating plant, we were getting a zero point 0.1 volt of change in the output. So this was the specifications of the sensors which we use. But we cannot use the sensor. We cannot use the sensor as directly, as we will be needing some here like signal conditioning circuits also, just as to amplify this. Uh, so because this what we needed, this we needed, but sensitivity of the sensor was 10 millivolt per degree Celsius. So in order to change the sensitivity to zero point 0.1 volt per degree Celsius, what we did, we realized is using a signal conditioning circuit. So whatever the sensor output we were getting, we pass it through two inverting amplifiers. So this was output, this was V naught. So here we can use that feed bias current compensation, both the op amps. So here we were getting a gain of -1 at the first op amp. Gain. So if we are having a signal like this, so we were getting a signal like this. Then after that we can attenuate this signal, and finally attenuation at the same time we are also uh, inverting the signal again. So what will happen? The signal will become like this, little smaller in magnitude. So the attenuation factor we used here was 10 by 100. That was 1 by 10.1 factor. So was used here in order to meet the sensitivity of the temperature sensor. So then we saw error input, we saw sensor and signal conditioning circuit. Now we'll talk about what we learned in this week 7 lecture. As so we talked about heating circuit first. Now we have seen the sensor signal conditioning circuits and the error detector. Now we will go towards this heating plant. So how we can realize that? So heating circuit. So we saw that we use op-amp and a transistor for the heating circuit, but then the question will arise why we need op-amps for the transistor circuit. We not directly use transistor circuits for realizing this heating plant. So we'll see if we see it's a transistor simply connected with a zero point 0.1 ohm 10 watt resistor. Okay, and we are giving some input. V, this is R, which is let's say 20 ohms, and we are given VCC is given. Okay, that is let's say 15 volts. So what will happen? So since we are applying, and we will make sure that this input voltage, whatever we are giving, it is greater than the diode reverse bias voltage, that is zero point 0.7 volt. So there is a diode here inside that this transistor. So if this is greater than 0.7 volts, then this circuit will be working. So this transistor will be working. So for that, if V in is greater than zero point 0.7 volts, so what will happen? Uh, Hmm. So let's say we gave 15 volts here. So the drop across this transistor, based on the based on the transistor which we took, 2N3055. So based on this transistor's data sheet and ratings, a maximum drop can be 0.7 volts. So let's say 0.7 volts was there, so we will get a 14.3 volts here. Okay. So if we get 14.3 volts here, then uh, what will be the current with this? I. So current will be 14.3 divided by 0.1. So it will be 143 amperes. Okay, that is a very large current. So we don't want this much of large current. As the according to the data sheet of this current of this transistor, we can only have maximum current of I max can be 10 amperes. But based on this configuration, we are getting here as 14.3 volts, and thus the current is very high. So in order to control this current, we will be needing this op-amp circuit. Okay. Then how? So what we did? So we used op-amp, used an op-amp, and we gave supply to V in, and we basically realized a voltage follower using an op-amp, so which can maintain a voltage at the output of its, or we can say at the emitter junction of the transistor. Okay, so this was again 0.1 10 watt resistor. Now in this case, what will happen? So we are giving some input. So based on that, this op amp, this transistor will be on. So it will be conducting current. So this current will be conducted, but at the same time, what this op amp will do, this will basically uh, will be acting as a voltage follower. So there will be a concept of virtual short here. So V in will be here. We will get V in here. Okay. So based on that, we can say this V in is forced by the op amp. So op amp is maintaining this V in. So as we saw in the lectures also, if we increase this V in steps of zero point 0.1 volt, let's say zero point 0, then zero point 0.1 and so on, then accordingly we can get the current. And so based on the maximum current ratings of this resistor, or we can say the transistor, we can have, let's say, I max was 10 amperes as we saw in the data sheet. So based on that, we can have a maximum voltage V in across this resistor to be V in equals to 10 into zero point 0.1, that is 1 volts. So we will vary this V in voltage from 0 to 1 volt until it achieves its maximum rating, current rating of this transistor. So in this way, we were able to control the emitter junction voltage of this transistor, and uh, thus our transistor will be safe. So yeah, this was there. Then now if we talk about, then one thing we did that we saved our transistor from getting from damaging our transistor. We solved that problem. Now, but why we need a transistor in the first case? We need a transistor in the first case to realize this heating cycle. Okay, this heating plant. So for that, this transistor should raise its temperature as we as the current as it will dissipate the power, so that the temperature across the transistor it will be raised. Okay. So now, if we see the data sheet, or first we can say, let's say when we applied zero point 0.1 volt of voltage, zero point 0.1 voltage as the input to the op amp equals to V in, then we will get a drop of 15 minus 0.1 equals to 14.9 volts drop across the transistor. Okay, so then what will happen? The power dissipated across the transistor, it will be equal to Vi, which is 14.9 into what was the current when zero point 0.1 volt is being given. The current will be zero point 0.1 divided by zero point 0.1 ohm resistor. That is the zero point 0.1 voltage across the resistor and the zero point 0.1 ohm resistor. So it will be 14.9 watts. Okay. Now we achieved for a certain value of V in, that is the input which we gave to the op amp, we achieve some power. So we can again, if we increase V in, then what will happen? Then IE will also increase. Okay, and that is the current through the resistor. So let's say, example, we made V in equals to 0.5 volts. So what will happen? Although the drop across transistor, V transistor, we can say drop across transistor is equals to again 15 minus 0.5, which is 14.5 volts. So this drop across transistor decreased, but the current IE, or we can say current through resistor, current through resistor, that is a resistor of 0.1 volt. That will be uh, we have a zero point 0.5 volt V in, which is divided by zero point 0.1, so our current will be 5 amps. So the power dissipated now will be 14.5 into 5. That will be around 72.5 watts. Okay. So we saw that as we increase the V in voltage, as we kept on increasing the V in voltage, our current through emitter current is increasing. Although the voltage across the transistor is decreasing, but our current through the emitter is increasing. So that is ultimately leading to the increase in the power dissipation through the transistor. So based on this power dissipation, we can say how much percentage, how much change in temperature is getting being absorbed at the transistor. So based on the data sheet, the dissipation factor, dissipation factor, or we can say power dissipation factor. So power dissipation factor, we can say that it is 0.657 watts per degree Celsius. So we had 14.9 watts of power dissipation. So based on that, the percentage degree Celsius change was 14.9 divided by 0.657 degrees Celsius, which is equals to, or we can say the temperature which initially what was there when we applied a 0.1 volt voltage across the as the input to the op amp. Then the power dissipation of the this transistor was, or power distribution of the transistor was 14.9 volt or 9 watt, and based on that the temperature rose, or the temperature at that moment was 14.9 divided by 0.657, which is uh, we can say 22 degrees Celsius. But in the data sheet, it is mentioned that we have say, it is given from the starting point as 25 degrees Celsius. So the total temperature will be 22 plus 25 equals to 47 degrees Celsius. So for zero point 0.1 volt, V in equals to zero point 0.1 volt, we got a rise of 22 degrees Celsius that ultimately leads to 47 degrees Celsius as at the output of the transistor. So if we talk about 72.5 watt, it will be high. So in this way, we can realize a transistor. We can use transistor to mimic the heating plant, the behavior of a heating plant. So we saw this. Okay. Now we'll come to controllers. So in this, we will see on-off controller. Then there will be proportional controllers. Then proportional integral controllers. Proportional integral controllers. Then it will be PIP controllers. Okay. So so in week 6 also we saw a little about these controllers as when we talk about this on off controllers. So how we realized this on off controllers using a positive feedback, that is basically a Smith trigger. So using Smith triggers we realized this. So what we did, we actually we had this. uh, positive feedback configuration for our op-amp. This is 100K. Here we were giving the error input. Here we were getting output, and this was being fed to the heating plant. Heating plant. So this was V plus. Okay. So 100K R2. This is R1. We chose that as 180 ohms. So we saw this on-off controller. So what is happening? This is basically an inverting spin trigger. As we saw this also, that based on the threshold limits, the upper threshold and the lower threshold, if our this is changing like this, input is changing like this. So what will happen once it reaches the upper threshold, then it will go down. Once it reaches beyond the below the lower threshold, then it will switch on as high. Okay, again it will be high until it reaches again the upper threshold. So like this we achieve this uh, output. So this is the very basic on-off controller, and the output, or we can say the V1, this V1 input is given by V1 equals to R equivalent by R3 V01 plus R equivalent divided by R1 V plus. So this is the relation of the threshold limits. Threshold limits. So when we are looking at the upper threshold, then this V naught will be plus V set. Otherwise, it will be minus V set. This will be either plus minus V set. Based on that, we can get the lower and the upper threshold. So this we saw. Then we also then after getting the output from this on-off controller, we use one signal conditioning circuit. As we know that why we needed signal conditioning circuit. Signal conditioning circuit at the output of on-off controller. So this was done because our heating plant is taking only heating plant 1 volt max, we can say, um, max input. So we cannot give beyond that. But the output here we were getting as plus minus V set. This either it was plus V set or it was minus V set. So in order to reduce that output of this on-off controller, we made a signal conditioning circuit using again an op-amp. So this was for the feedback bias current compensation, and then we had a variable gain, a variable resistor here R5, which was, and we had R6 also. Okay. This was V0. So this was the output from the our on-off controller, and here we are this V0. Then we can give finally to the heating plant after reducing the voltage of the output of the on-off controller. So what will happen? This is 1K, and this is like we have maintained 15% of 100 K ohm. Okay, I will write it clearly. So this is 15% of 100 ohms, 100 k ohms, kilo ohms. So what will happen? The attenuation it will provide to the output will be, so if we are getting V naught 1 as 15 volts, attenuation will be R6 by R5, which will be 1k by 15%, we can say 15% of 100 kilo. So we will get 1 by 15 as the attenuation factor. So attenuation factor here is 1 by 15. So output V naught we will get as V naught 1 into 1 by 15. So since our V naught 1 was 15 volts, so we will get as 1 volt. Okay. And one more thing I forgot to tell, this R equivalent is basically R1 parallel to R2 parallel to R3. Combination of R1 parallel R2 parallel R3. That is this one and this R3 resistor. So, so in this way we can realize this heating plant circuit. Sorry, not heating plant circuit. We can give input to the heating plant circuit using this on-off controller. We realized an on-off controller here, and we used also a signal conditioning, a small signal conditioning circuit here. This one, so as to decrease the voltage of the on-off controller, as we are getting something, some output from the on-off controller which is very high, that is 15 volts. So that voltage uh, cannot be directly given to the heating plant circuit. Since its maximum voltage is 1 volt, so based on that we use the signal conditioning circuit. So based on your heating plant circuit requirements, we can use this. We can develop our own signal conditioning circuits as well. So it will depends completely. It will depend completely on your requirements or whatever your requirements are for your heating plant circuit. So then after this we will come. We saw that we come to proportional controllers. So in proportional controllers, how they work? So the output of these proportional controllers are directly proportional to the error. So we U of t is equals to Kp E of t. So this Kp is proportional constant. Proportional constant. So we saw this also, like different conditions. As I will draw it here also. Uh, where by varying this Kp we will get different outputs. So say, let's say as we considered a tap here, and we had to fill this, you can say a bucket. So water was coming from here. Let's say this was the water level. So then what will happen? We had a valve which is connected to a rope A and B. We are having a ball-like structure here. So the water will come till this point A. So this A B. So this will be RXP, which is proportional value. Proportional. Since Kp we know, the output of this circuit. This let's first say about the output of the circuit. The output of this wall system is basically Y. Uh, Y equals to A by B into X. We saw this in week 6 also. This A is the length of this much of length of the rope, and B is the this part of the rope. So we had this wall, and this was the X distance, like this the how much. Uh, how much this valve is that inside the this was X inside the pipe. So X was the position of the valve inside the pipe. A is the first half of this rope, and B is the length of the second half of the rope from the fulcrum. So this was KP. In this case, this was KP, and we know what is XP. XP is XP equals to proportional band is 1 by KP. So we have some value of proportional band here. So, but if we change the position of this fulcrum, we change the position of this fulcrum. Let's say now we are giving more space to A and very less space to B. So this proportional, let's say we have water area. So this proportional band will be decreased. XPY because KP is A by B. We are decreasing B, the length of the other half of this wire, and we are increasing A. So ultimately, this will increase. So if Kp is increasing, then since this is inversely proportional to the Xp, that is the proportional band, so we are the proportional band is decreasing. Xp is decreasing. Okay. So in this way, we can change our proportional constant, that is Kp, and based on that, this Xp and all those things will change. So another configuration was also there in which that was the other way around. We had the same system, but now the fulcrum was towards the wall. That is A was reduced. Okay. So in this case, the XP will increase. XP will increase. So KP will decrease here. XP will increase here. Okay. Now this was about how we can see, how we can perceive a proportional controller, but then how we can realize this proportional controller using op-amp circuits. For that, we use two inverting configuration, two inverting amplifiers op-amp like this. We have one inverting gain amplifier. Then we have again inverting gain amplifier. So this resistor is can be varied. So we have kept this 10% of NK. This is 10K. This is R2. This is 100K. Okay, this is R1. This is 100K. Here we have our bias current compensation, and we are giving error, and we are getting output from this, and this is being this is being given to heating plant. So instead of on off controller, we are using a proportional controller here, heating plant. So what will happen? This is V naught 1. So simple. It is very simple. The error, whatever, let's say we were giving 10 volts here. So it will just convert it into minus 10 volts because the gain of this first inverting amplifier is 1, minus 1. Then again it will pass to the second op amp, which is acting as an attenuator. So what will happen? It is having a gain of 10% of this by 100 by 10. Sorry, 10k. This is k. 100. So this will get point 0.1. So this will attenuate this minus 10 volt signal to point 0.1. That will make our V naught, the output voltage, to minus 10 into point 0.1, which is minus 1. Minus or minus 1, because this is itself an inverting amplifier. So this will be, that will be 1 volt. So we'll get a 1 volt signal here. So if we see, we have changed the sensitivity of the signal of the circuit. Initially, we were having for 100 degrees Celsius till 100 degrees Celsius, and we were getting a 10 volt range. But after using this attenuator, we were getting for 100 degrees Celsius change, we were getting a change. We were getting an output of 1 volt. Okay. So we got a new sensitivity here. This is new sensitivity of our power controller. We can say system also. Then after realizing this proportional controller, we saw another controller that was proportional integral controller. So this is basically the output of this. We can say the output of this is directly proportional to the error, and also it is directly proportional to the integration of the error with respect to time. So if we combine both of them, we will get Kp E of t plus Kc integration E of t dt. So here what is happening? Uh, Initially, the proportional controller was just whatever the error was there. It was changing its output based on the error. So if the error will be high, it will be changing the its output. It will be making its output high. If the error will be less, so the output will be less. So it was like a linear we can say relation. But in case of integral controller, we add this integral controller. What will happen? It will also see. So what is this? Basically, it is the summation of all the past errors, all the past errors. So not only the present errors are being kept in mind, but also the history of the past errors are also being kept in mind. So if we see the let's say this was uh, the input, feed the input, then our this signal will be the controller output will be like this. So it will settle somewhere near the settle point. This is the settling point. It will settle here, this point. So uh, so this controller is basically keeping in mind the history or the this areas also. Okay. So this is you can say uh, so this E of t is basically shown in this shaded area. This are all E of t. So he is first adding this is a positive area, then sorry, this area is being added, then this area, then this area, then this area. So after adding all those things, then we are getting the final output of the controller. So what happens if the error is large? If error is large, the integral mode will make the controller output fast. make the controller output fast. If the error is less, then the controller will become slow. Okay. So this is so how we can realize this proportional integral controller using opamps. So as we know, this is the combination of the proportional controller and the integral controller also. So we will have one part of the circuit will be taking care of the proportional gain. That is simple. This minus plus gain, we can have this compensation of bias current. We have then 100k at the feedback and 100k at the input. So this is acting as a proportional controller. Simple and negative gain amplifier, inverting amplifier with a gain of 1 minus 1. And we'll make one integrator circuit here, that is capacitor in the feedback will have 1 mega C1 1 nanofarad. So based on the values of these two, the time constant of this integrator will be decided. Error input. Okay, this is 100k here, and after after getting the output from this and this, we are basically using a summer to add both of the signals, the kp, the signal from the proportional controller, as well as the signal from the integrator. Then we are finally using an attenuator which is having a point 0.1 gain. This was summer amplifier. This was proportional controller, and this was integral controller. So this is about the proportional integral controller. So then we saw the simulations also in the this in multi-sim, that online simulator, and we also saw the realization of this using the PCB board. So all in all, today we learned about uh, basically we wanted to design this thing started from week 6, that what we wanted to design. We wanted to design a temperature on off controller. So for that we had a feedback system in which we will be using a controller, a heating plant for which we are controlling the temperature, and then a sensor which is basically this sensing the heating plant temperature, and then a signal conditioning circuit for that sensor, and this signal is then feedback to the error to the controller. This controller is receiving an error input from the input side. So we wanted to realize this system, but how we can realize this using a op-amp circuit, using an op-amp circuit. So first we saw that we realized this error detector, where we use uh, a simple differential circuit, so differential amplifier circuit, and with a gain of 1, we can get the error signal. Then we saw that we needed a sensor signal conditioning circuit for our sensor. So sensor which we used in this on-off controller was LM35 temperature sensor, but the sensitivity of this sensor was 10 millivolt per degree Celsius. So for that we needed zero point 0.1 volt per degree Celsius. So this can be varied according to your uh, requirements. But here we wanted to magnify the signal, they magnify the signal from the temperature. That's why we use zero point 0.1 volt instead of 10 millivolt per degree Celsius. So for that we use two inverting amplifiers. You can use a non-inverting amplifier circuit also, uh, having the same gain as this two inverting amplifier systems, the opamps. And then we got a final attenuation factor of plus point 1. Okay. Then we wanted to mimic the heating plant that as the temperature change in a heating plant. For that we use a transistor. So we cannot directly use a transistor, and it was limited by its current capacity, by current carrying capacity. And then for that we in order to limit this current capacity of the transistor, we used an op-amp circuit. We used an op-amp circuit in a voltage follower configuration. For that, we gave one input, and this was input was being forced by the op-amp at the output of this emitter junction of the transistor. So we saw that by changing the V input voltage V in steps of zero point 0.1 volt, then we can vary this V in voltage across the emitter transistor. Based on that, we can vary the current, the emitter current through the resistor zero point 0.1 and 10 volt. So we knew that the maximum current which a transistor can handle was 10 amperes. So for that, the maximum current which the maximum voltage which this emitter junction can have can can go up to is 1 volt. Okay. So for that, the drop across the transistor will be this. So then we saw that how the power dissipation will be there in the transistor. So for 14.9 volts of drop across the transistor, we were having a current of zero point 0.1. We are having a current of 1 ampere. So based on that, we got a power of 14.9 volts. So as we will keep on increasing this V in, our emitter current will be increasing. So, for example, we took zero point 0.5 volts as the input to the op amp. For that, we saw that the drop across the transistor was 14.5 volts. So, based on that, if we calculate the power, although our emitter, uh, what we say, the drop across the transistor was less. Like it was 14.5, but earlier it was 14.9 volts. 14.9 volts. So, what happened? So then what happens that the total, but overall the total power got increased. That the dissipation of the power got increased. That was 72.5 watt. So similarly, we can increase the input voltage, and based on that, the emitter current will increase, and thus we can increase the power dissipation through the transistor. So using the dissipation factor which is given in the data sheet of this transistor, that was 0.657 watt per degree Celsius, we were able to get to see that it was the temperature was increasing across the transistor. So based on the power dissipation, we can increase the temperature of this transistor. So thus we realized a heating plant circuit using that transistor. Then we came to the controllers. We saw that on-off controllers are there, proportional and proportional integral controllers. So we realized this on-off controller also that was using a split trigger, but it was an inverting split trigger. As once it goes up the upper threshold, the output will be minus V set and vice versa. So we also realized this output equation for the not output the threshold limits for this split trigger, and this R equivalent we see that it is equal to R2 parallel R3 combination. Then we needed a signal conditioning circuit for this heating plant because the heating plant can only handle 1 volt max input. So for that we again used an attenuator having having a gain of 1 by 15. So based on that we got an output of 1 volt. We can get a output of, yeah, we get an output of 1 volt from this on-off control, which can be fed to the heating plant. Then we saw the proportional controller, and then we took the example of this wall systems. By changing the A and B length, we can change the KP, and thus we can change the XP, the proportional band, these constants. And then we see this using the how we can realize this using op-amps. So we basically change the sensitivity of our circuit by using these two op-amps. One was inverting and another one was inverting as well as attenuating also. Then we came to proportional integral controller. So this was doing the function of proportion controller also, as well as it was also integrating the error signal. So it was summing all the past errors. We and thus one property of this integral controller is that if the error is large, the integral controller will this integral mode will make this controller output fast, and if the error is less, then the controller output will be slow. Okay, then we saw that how we can realize this circuit using these op-amps. So we use proportional controller here and the integral controller, and we just used a summer amplifier to add those both of these inputs using this summer amplifier. Then finally we use an attenuator with a gain of zero point 0.1 to so that we can feed it to the heating plant. This heating plant. So this was all about the compilation of week 6 and week 7 basically. Then now we'll move towards assignment questions. So if you have any doubts in assignment question, you can ask. If you have doubts in any previous assignments also, then you can ask that also. So we'll go one by one. So yeah, the I think the questions were quite easy in these assignments. So the first question is very straightforward. In the video, the heat is generated on. So we have completely discussed about the heating circuit and uh, how we made that and all of those things. So you can answer this easily. So this I don't think you will be having any doubt. Then the next question. So what is the role of 10 watt resistor in the heating circuit slash? So if you see the options, to provide necessary voltage drop across the resistor, to support for large amounts of current without heat dissipation, to provide heat required for the circuit. So we know that this thing that to provide heat required for the circuit, we are doing this using another thing that we are very clear about it. Okay, because we have just discussed a lot about that. So then we are left with the other three options. So first is to provide necessary voltage drop across the resistor. So I think or the second is to support for large amounts of current without heat dissipation. So in that this was zero point 0.1 ohm 10 watt resistor. So basically the power ratings we can say that the maximum voltage we can handle is 10 into zero point 0.1 under root voltage. Okay, this is let's say this was the power rating of this resistor 10 watts. So what will happen? The maximum voltage which it can handle is 1 volt. Okay, max. So now if you will be having a less so this the voltage across this can be maximum up to 1 volt we can do. So if we are having a less voltage, let's say 5 volt, then what will happen? Then this voltage will be reduced. Or we can just for the simplicity of calculation I will say 4 watt. Uh, yeah. So it will be okay. It will be not okay. It will be 4 into point 0.1. It will be point 0.4. So definitely it will be 2 by root 10 something. So it will be less than this. The voltage will be less than this. So what will happen? Let's say in this case it was 1 volt max. So 1 volt, up to 1 volt we can get here. In the first case, when the power is 10 watt. So the current which can be passed through this is 1 by 0.1, that is 10 amps. But if in the second case when the power was less for this resistor, what will happen? The voltage drop across the resistor will be less. So if we say about the maximum current which it can pass through it, it can withstand this. It will be V upon 0.1. So this V has been dropped now because the power rating has been dropped. So this whole thing will be dropped. So we will be getting a less value for maximum current across the which this resistor can withstand. So I think based on this discussion, you can answer this question. Now moving to the third question, the transistor used in this application is that is I think simple, very simple. So since we're talking about the power dissipation factors and all those things, so I think we need transistors similarly like that, which can withstand like a large current, you can say. So you can go and check which type of transistor can withstand large current. I think it's very straightforward. The next question, fourth. Okay. For the circuit shown below, compute the total current supplied by the source. Okay, the plus 12 volt is given as the source voltage. This beta factor is 60. No, consider op amp is ideal. So they are saying the op amp is ideal. So we have to calculate the total current, output total current supplied by the source. Okay, supplied by the source. So one current. So this is the source. This is I. Let's say this is the source current IS. Okay. One current is being diverted through here I1 and another current is being diverted through here I2. So we'll go first towards I2. For I2. So we know this Zener diode is being used, so it will maintain a 5 volt here. So what will happen? The I2 will we can easily get is 12 minus 5 divided by 50k. Okay, which will be what? 67 by 50 milliamps something. Okay, you can calculate. Then I1. So I1 will be for I1. What will be I1? So we have a transistor. We have 5 volts here. So based on this virtual short, we can have 5 volts here. Okay. So then what will be this current? This current is basically IE. So IE will be 5 by 100 amps. But now that is basically 50 milliamps. But now we are talking about I1. So I1 is what? The collector current. The collector current of this transistor. So we have been given beta. Beta is very low here. That is 60. So, but normally we have IE. If we have to convert this into this, what we say, we have this relation. We know this relation IC equals to alpha I, and alpha is beta upon beta plus 1. Okay, I. We know this relation. So based on that, we can get IC equals to 60 by 61. I. So this will be so IC will be little less in this case than IE. So by IC equals to I1, so by adding this value and this value, we can get the answer to this. So if this beta value is not given, so you can then in that case you can consider simple that IE is approximately IC. But if beta is given, then this thing will be. Then they are asking for the precise answer. Okay, so I think no doubt in this question. We'll move towards the next question. Question 5. So in continuation with the previous question, consider the transistor as a power dissipation factor of, okay, they have given power dissipation factor of 0.657 watt per degree Celsius. So does the transistor produce a noticeable temperature? Okay. So they are basically asking us to find the temperature of this, but based on the previous question. Okay. So, okay, let's say okay, what now? So we need a power. We need power across the transistor. So we know that 5 volt is mandate here. So this voltage is 12 volt. So power across transistor will be power across transistor. That should be I. So V will be what? 12 minus 5 volts into I. I whatever we got I as 5, 6, 7, 4. So based on the options here, it will be in milliamperes. Okay. So let's say just averaging all these answers. Let's say we we take it as 120 milli. Let's see. We'll see if there is a any noticeable change in the temperature. Okay, because I'm not telling you the answer for this question. So I'm just averaging this and then let's say what is the power. 740 million. So based on this, if we have 0.94, this is watts divided by 0.657. So in this case, it will be 1 degree Celsius something it will be there. But if we go a little less than this 120 milliampere, then will it, so if this thing will be less than 0.657, then definitely the temperature will be less than 1 degree Celsius. So I think based on that, based on the answer here, you can get the answer from here also. So if it is very less, then the answer is no. If it is 1 degree Celsius, then the answer can be yes. I hope this is also clear. So question 6. Compute V naught for the given circuit. V naught is, this is V naught. So they have given us a transistor here, Q1 transistor, an op-amp, 6 volt supply, 2K, 8K resistor, 8K resistor. This is a 40 volt it's supplied to the collector of this transistor Q1. Okay. So how you will approach? Uh, we have a negative feedback circuit here. So we have 6 volts here. We have 6 volts here. So we can get current also. The current will be 26 by 2K, that is 3 milliamps. Since that current cannot go through this, it will be coming from this side. So this will be again 3 milliamperes. So if we use, uh, yeah, so I think if we use V naught or, oh wait, so we are supplying current from here. So if we use this V naught plus okay, minus 8K into 3 milli equals to 6 volts. Fine. Then V naught will be 6 plus this will be 30 according to me. Yeah. This will be 30 volts. Okay, I've given answer for this. Okay, no issues. But yeah, it is a very simple question. So you can solve this like solve it like this. Okay. Now Moving towards the next question, seventh. For the circuit shown above, compute the range of input. Okay, for the circuit shown above, compute the range of input voltage required at the op-amp non-inverting input terminal. So they are saying at this terminal, non-inverting terminal, we generate 5 milliampere to 10 milliampere current through 8k resistor. So they are saying, okay, we have to generate a current of 5 milliampere to 10 milliampere through 8k resistor. So if that is the case, we will just first we will go for 5 milliamperes. So in this case, if the current is 5 milliampere, 8k into 5, then uh, we need to get the op-amp non-inverting terminal. So that is this is basically op-amp non-inverting terminal voltage because this is virtually short. So it will be V plus. So 10 milliamperes, है ना? Or we can say, or we can do it like this. For 5 milliamperes, the voltage of drop across 2 kilo ohm resistor is this resistor is into 2k. It is basically V plus. That will be 5 10 volts. Similarly, for 10 milliamperes, V plus will be 20 volts. So yeah, so that is the answer basically. So we can solve this also. So we should know we know this current across this resistor, and we have to find this voltage, this V plus, that is the input non-inverting side, non-inverting terminal voltage of this op amp. So based on that we can calculate this based on the current flowing through this 2 kilo ohm resistor. Then the eighth question. So what is the op-amp configuration used in the video for implementing on-off controller? So I have mentioned this in this session also, and you can again check the video. So this is straightforward question. This answer to this question. Then the next question is, design the circuit shown below to provide a low threshold voltage of 0 volts and high threshold voltage of 10 volts. V plus and V minus are plus minus 15 volts. So we know the threshold. Let's say the equation for the thresholds. Threshold of this, if you recall, this is basically an on-off controller circuit, and this is the error input and threshold V1. We saw in the lectures also. That is basically uh, R equivalent V naught 1 by R3 plus R equivalent V plus by R. Okay, I think this equation is familiar. Where R equivalent is what? R equivalent REQ is EQ equals to R1 parallel R2 parallel R3. So now they have said, so this is threshold. So if you talk about lower threshold, then uh, V1 they have mentioned it as 0 volts. This will be 0 volts. So 0 volts equals to what? R equivalent V naught 1 R3, and here this will be what? This is V plus only, but this V naught will be minus 15 volts because we are talking about lower threshold. Hmm. So what will happen then? Let me yeah. So minus 15 volts. So it will be R equivalent by R1. V plus is yes, so it will just this will be 15 by R3. R R equivalent will be cancelled. This will. This is common. So this will be V plus by R. So this V plus is equal to this 15 volts. So we can see that the R1 equals to R. So one thing is this. Now the next thing is the lower threshold, or we can just say since we don't know, since they have not given V plus what is the value of V plus, so we can simply keep this equation as it is, and based on the options we can say what is the values of V plus accordingly. So now we have another threshold, that is 10 volts. So for 10 volts it will be, this will be plus 15 P naught 1 by R equivalent plus V plus R equivalent by R. So here also solve by solving this equation, and you can get what is R equivalent, and based on this so V plus which we used here, so and on based on the equations also, based on the this options also, we can consider V plus equals to 15 volts, but that you can yourself check, if we will make V plus equals to 15 volts, then will one of the answers will be satisfying in these options. If it is so, then it is fine, you can go to there, because here nowhere it is mentioned what is V plus. Okay, it is mentioned, yeah, V plus is there, V plus is given 15 volts, yeah, then it is fine. Okay, okay, okay. Yeah, it is mentioned. So V plus is 15 volts. Okay. So then V plus and V dot 1, the output of this voltage plus minus 15 volts. So this is cancelled out. So R3 equals to R1. And here also V plus 15 15. So 10 by 15. Uh, then R equivalent. So 1 by R1 R3 are equal. So this will be 2 by R2, we can say. And using R equivalent, this expression, we can solve what will be the values of R1 R2 R3. Okay. This question is okay. So yeah, next question. In the video, the proportional controller was implemented using dash of configuration. So again, this is very simple. We know that using what we used, since we use an attenuator, and we also wanted to use inverting inverting amplifier, but they're still mentioning in the video. So, but we can realize this using other ways also. So that also I have mentioned in my this lecture, and that was mentioned in the main lectures also. So this is also okay. So what is the scaling factor used in the circuit for representing temperature using voltage? So this is straightforward question. Yeah, select the suitable op-amp-based error amplifier configuration. So we know that. So we are talking about error amplifier. So basically, this circuit which we were using, this was error detector. Okay, for that which we use, so we use something. So based on that, you can use a signal condition circuit, or you can change the resistors of that circuit, so to amplify that error signal. So based on by seeing the lecture, you can answer this also. This is also very easy. Hmm. So I think this is done. This is, this is also done. So if any doubts in the assignments, you can ask. So yeah, one question was there. So assignment questions are done. So one in the previous lecture there was one question that was from the week 4 assignments. So it was a simple this circuit. This was grounded, and this was given a supply of 3 volts, and then a positive feedback. This was 1k, this was 1k, or this was R, basically R, and we were asked to give the voltage, the output voltage. So this was minus 20 volts, this was 20 volts. Okay, so this was there, I guess. Hmm. So one person was having doubt in this question, as he was getting, although it is similar, although it is simple that we'll get 20 volts output, but in simulation he was getting, I think, 3 volts plus 3 volts, and that he was using that multi-sim simulator, online simulator that is being used in lectures, online simulator. But then I checked with Tina TI. Tina TI is itself software for use for realizing these analog circuits. So based on that, I was getting this this output only, but he was getting 3 volts. So there was some glitch in that, maybe some glitch in the software, or he has not, or I think he has not done that thing properly, the circuit. So, but yeah, the answer will be 20 volts itself. So this is okay. So now there are some extra. There are some two extra questions which are there. Extra questions. We'll just see. So these are just some application of this opamp. So as we are as we this lecture, this what we say subject, this course is about the applications of opamp. So one of the very widely used applications of opamps is the linearization circuits. So opamps are used for linearizing, so linearizing the whatever we are given input to that. To the op-amp. So we can say, if you want to realize strain gauges, if you want to use strain gauges for in bridge form, like let's say we have this four resistor bridge form circuit. We want to use this. These are all strain gauges. R1 plus delta. Let's say this is R11 plus delta. Let's say this is R something. This is R simple. So this is two bridge strain gauges. Two strain gauge system. So if you want to realize these outputs of these circuits, or we have RTDs also, resistance temperature dependent circuits, RTDs, or many more other circuits where one of the values, one of the resistor values is changing. So how we can linearize that? So this is also having similar. This question is also having similar things. So this is basically linearized with circuit, which yields V naught equals to minus R Vref delta by R1 plus R. So we have output as minus R Vref delta R1 plus R. So how this linearize this? So as we will keep on changing this resistor. This resistor can be any temperature sensitive resistor, or voltage and any pressure sensor, pressure sensitive or vibration sensitive, something, some sensitive resistor we can use here. And based on its variation, we need, so this was varying 1 plus delta, something like that. So if you want to get output which is only directly proportional to delta, so this is basically we are linearizing this input, whatever we are giving input. So how we can, so the answer question is saying what, how we can realize this V naught equals to, so this we have to prove that. So if we see this circuit, just so this R1 is there, so we know this voltage V minus and this V plus, these are equal. V minus equals to V plus. So the current through this and the current through this will be same. Okay, let's say this is I2, this is I1. So I1 equals to I2. So if we use KCL or KVL in this, at this point and at this point, so we can have so this let's say we can, this we can denoted as V1. Okay. So so it will be V1 minus Vref divided by R1 plus V1 minus V0 divided by R1 plus delta equals to 0. We have two paths. I equals to, sorry, not 0, equals to this voltage, this current I2, that is V1 minus Vref by R1 plus V1 by R. Okay, this we have. Or we can say like this also, I1 will be, let's forget about this. This will be the second approach will be easier than this. So what we can say, the I1 current will be, or what? This is V naught. Okay. So wait. So we have I1 as we have I1 as V naught minus V ref. Um, yeah. So V naught minus V ref. We are adding both these operations, R1 plus R1 plus delta. Okay. And which is equals to I2. What is I2? This is I1. I2 is what? I2 is V ref minus 0 by R1 plus R. So this whole current is going through this whole branch I2. This current is going through this whole branch I till V naught. Okay. So what we'll have, V naught equals to R upon R1 plus R V ref to delta. So by solving this, we get this. But then the question is also saying what is the disadvantage? The disadvantage, we can say we are having disadvantage of the circuit. So the disadvantage is that we are having less gain here. The gain is very less, as it is R upon R1 plus R. Because of that, this since we have seen that in these controllers also, even in sensors LM35, in the temperature on of controllers, we have used signal conditioning circuits either to attenuate or we have to amplify that. So in this case, as we know that the gain was less, so we will be using a gain stage also. So unnecessarily we will be using another stages, and the things can be like so yeah, the gain stage we will be using. This is one of the disadvantage of this circuit. So yeah, so what we saw in this question was like we saw linearized this circuit which can linearize this changing resistance value, and we can get an output which is directly proportional to only delta. Okay. Now the second question is the extension of the previous question. So in this question we are getting an output of V naught equals to R2 Vref delta by R1. So they are saying we have to realize this thing using this circuit. So this has been patented a long back. Okay. So this was there. Okay. So just see the question. So again, so we know that this circuit we just saw. So or we can say at let's say this is one, this is two. Okay. So at one node 1, we have 0 minus Vref by R1 plus 0 minus V naught by R2 plus 0 minus V naught upon R1 plus delta equals to 0. Okay. R okay, okay. Yes. Okay, one clarification is there. This is only R. This is R1 plus delta. Maybe okay. So this is R1 plus delta. So based on that, this is the yeah RKVL equation. So if we talk about that too, we have minus V ref by R1 plus 0 minus V naught 1 divided by R equals to 0. Okay. So then by combining these two both and substituting it for this is V naught 1. Substituting it for V naught 1, we'll get V ref 1 by R minus 1 plus beta by R1 equals to V naught by R2, which is basically V naught equals to V ref R2 by R1 delta. Okay. So using one another op-amp, we were able to linearize this circuit and we were also able to increase the gain of this circuit. So gain has been increased. So gain has been increased. So we saw these two questions. These when we are going for linearizing circuit, so we need that. So basically, this is a differential amplifier configuration and how we can utilize this potential of the differential amplifier by using this configuration also. These are very simple configuration, but at the same time very useful. So then I think it's all about today's week, week 7. So we talked about we talked about this week 7 by using the things from week 6 as both are connected. So we wanted to build a temperature on a controller. So for that, we use this system. We followed this control network, which we are having a system input. Then given to a either input is given to a controller. Then it is then given to heating plant. Then it is being feedback to a sensor and a signal conditioning circuit. And then yeah, we wanted to realize this on a controller. So for that, we saw about this error detector, which we saw in this week 6 also, implementation of error detector using differential amplifier. Then we saw the implementation of sensor signal conditioning circuits where we wanted LM35 to be sensitive according to our values, that is zero point 0.1 volt. For that we used a signal conditioning circuit having a attenuation factor of zero point 0.1. Simple, we used two inverting amplifiers. Then we realized heating circuits. So heating circuits were for heating circuit we use transistors. So transistors we cannot directly use them because of the limitations of the because the current limitations for them, as through them only 10 ampere current was there. So in order to keep in mind that current limitations, we used op amps. And the op-amps, what it did basically force the resistor, the voltage across this resistor to be a constant value. Based on that value, we can control the current to the transistor so that we can limit the current to its maximum value, that is 10 amps. So we saw this. Then we saw that power dissipation of the transistor and how it is, if we are increasing input voltage, how the current is changing, and how the power is dissipating more. And based on this dissipation factor, we can get the temperature uh, of this transistor. Then we saw the controllers on off proportional and proportional integer. Then on off controllers, we used on off controller we used simple Smith trigger, where it was inverting Smith trigger. In this case, this was the input which we were given, and this was the reference voltage, and threshold was given by this equation. where R equivalent was given by this. Then there was a need of signal conditioning circuit also, because it can't take only up to 1 volt max. So that will depend on your requirements. So we use one again an attenuator of 1 by 50 factor. So we attenuated and we got 1 volt max input, which we can give to the heating plant. Then we saw a proportional controller. It was directly proportional to the error which was given to it. Then we saw these different valve configurations and how this proportional constant can be changed just by changing this A and B factors. But then we realized this controller, this what we required, what was required for our application, that is using these opamps to inverting amplifier configuration opamps we used, and then we realized this heating plant. Then we also saw the proportional integral controller, where the integrator and proportional constant both are used. Then by solving all the past errors, we can realize this proportional integral controller. And how we can realize this OPA, we also saw that by using integral controller, proportional controller, and a summer amplifier with an attenuation of 0.1 gain. So this was there. Then we saw the assignment questions. We discussed that. Then there was one down from the previous week for assignment in the previous session. Then that is also we saw, and then we looked into some extra questions where linearizing circuitry was used. That can be applied in strain gauges and what we did piezo resistor materials for linearizing their outputs. So we saw one configuration. We saw that its disadvantage was less. It was disadvantage was that gain was less. So we realized another configuration where we can increase this gain, and the same time achieving the linearization. So I think that's all. So yeah, thank you.